Okay, we've seen how this transformation appears to rotate everything. We've left the question of whether it's a uniform rotation, whether every vector is rotated through the same angle so that they maintain the same spacing all the way around the circle. We've left that question open. Okay, you can think about that. And you can you can figure that out if you are ambitious and really want to do so, but there's no need to do that right now. Okay, now what I've done a little, what's new on this picture, this I believe is new, and I've numbered the vectors 1, 2, 3, all the way through 12. And then I've numbered the images of these vectors 1 through 12. Okay, now down here, I've got the picture of the transformed vectors. And I've actually got picture of, the picture actually includes all of the 12 transformed vectors. But what we're going to do first is we're going to find the white chalk. We're going to look at the first vector, the 1, 0 vector. We see that the image of that vector under this transformation, transformation 2, is 2, 0. Okay, well, that's this vector here. Now I've lined this off. The scale here is not identical to the scale here. This is 1 unit on this picture, and 1 unit on this picture is significantly bigger. And the units on this picture aren't all that uniform, but we still get the idea. Okay, so what we do is we transform vector number 1 here, and we get 2, 0, which is this vector. So I'm going to put a 1 here. And then we transform the second vector, just do the simple matrix multiplication, and we get 1.74, negative 1.5. Here's 1.74, negative 1.5. So vector 2 would be about here. And then vector 3, 1, negative 2.61, well 1, negative 2.61, that puts it about here. And I didn't leave myself enough space at the bottom here. But number 4 is here. That might be a little hard to read. So the first 4 vectors are like this. Now, there's a difference between what this transformation does and what this one does. This transformation simply rotated everything and maintained the same length. This transformation, acting on exactly the same vectors, does something a little bit different. In the first transformation, the vectors maintained their order. They were rotated, but we went, okay, if we go from vector 1, 2, 3, 4, their images, the images of those vectors, down here 1, 2, 3, 4, go in the same direction around the circle. They 1, 2, 3, 4 move counterclockwise here, 1, 2, 3, 4 move counterclockwise here. And that continues all the way around the circle. Everything moves counterclockwise. Here, not only is the image not a circle, because this distance is 2, and this distance are 3, but the vectors, the images of the vectors go in the counterclockwise, in the clockwise direction, okay? Here they were counterclockwise, I hope I said that right. Here they're counterclockwise, here they're clockwise. So the direction of rotation is reversed. And again, the sizes of the vectors change. This vector, which has magnitude 1, goes to a vector of magnitude 2. This vector, which has a magnitude of 1, this vector, number 4, which has magnitude of 1, goes to this vector, which has magnitude 3. So this thing is longer in this direction than it is in this direction. What we see from the first quadrant here is suggesting an ellipse. And when we complete all the vectors, we can actually verify that this forms an ellipse, assuming we know at this point what an ellipse is. Conic sections are not always covered in pre-calculus. Presumably everybody's had a calculus course, and presumably conic sections were covered in that calculus course, but that's not universal. So whether you know what an ellipse is or not. That is what we get, and it can be proven. You don't have to prove it. Maybe later in the course as an optional problem, and actually even now you could prove it. But you know, at this stage that would be a lot to ask. Okay. Okay, anyhow, we get these four vectors. Then, as we move around into the second quadrant, these are the images that we get, and we could easily multiply these. We can actually use a little bit of symmetry here. These second quadrant vectors are symmetric to the first quadrant vectors, in that each of these vectors has the negative of the x component of a corresponding vector over here. Number 5, which is an orange vector incidentally, has the same y coordinate as number 3, which is a green vector, but the opposite of the x coordinate. And similarly, number 6 is in the same relationship with number 2. What this means is, if we change the first coordinate of each of these vectors, okay, if we change the first coordinate, the image of this vector will become what we, well, I don't want to do that. I don't want to talk about that without actually writing it, so I'm going to abandon that, so just forget what I was saying. You can reason out by symmetry, and if you've had a good pre-calculus course, and hopefully a good calculus course where you used symmetry, understand the rules of symmetry and so forth, it's not difficult to reason out that vector 5 is going to have to be here. Now it looks like it ought to, since we've already established that going from here to here takes us from here to here. It looks like this is where we're going to be next. But that takes a little proof, okay? You have to establish that. You can't just assume that the pattern continues, although in this case it certainly does, and very often it does, but there are times when you think a pattern is going to continue and it just doesn't. And if you assume it's going to without proving it, you're going to be in trouble. Anyhow, that's, okay, then 8, 9, 10, 11, 12. Okay, so bottom line, and you can verify this, you can take every one of these vectors and apply the transformation, and you'll find that we go around the circle, around the ellipse, in the clockwise direction when we go around the circle in the counterclockwise direction. So that's just another picture of transformation, and in this case, again, the circle goes to the ellipse. Now I'll tell you a little secret. Any linear transformation will take a circle to an ellipse. Okay? Now that is, if we assume a circle is also an ellipse, which it is. So, you know, this circle goes to this circle, which is an ellipse. So the circle goes to an ellipse. And here the circle goes to a more eccentric ellipse. There's much more that could be said about transformations. The ellipses aren't always, don't always have axes. If you know what the major and minor axes are of an ellipse, and everybody should, but I'm afraid that, as I say, that often gets omitted. The long axis of the ellipse is not necessarily the x-axis or the y-axis. In this case, it's the y-axis. It could be rotated, okay? Because you can combine this kind of a transformation with this kind of a transformation. And we'll talk a little bit about that in a minute. This should give you a good, concrete pair of examples of transformations in a way that's not difficult to understand, especially if you come back to it every once in a while. Okay, well, that's all I'm going to say right now, but we will go on in a minute.